Alright, so for this problem, first we need to figure out the molar mass of the tin oxide. So from the formula that they gave us, and from the periodic table, we know that tin is 118.71 grams, and we have 2 oxygens, so we'll do 15.999 times 2. Add all that up, and we get a molar mass of 150.708 grams per mole. So if all we're given is a formula, we calculate the molar mass first, and then we're going to use the formula that's on the top of the page. So part over whole, that's going to be a common theme. So if we're doing the percent of tin, there's only 1 atom of tin or 1 mole of tin in the tin oxide. So we're going to do 118.71 grams, which is just tin, divided by the whole thing, the molar mass that we just got, the 150.708 grams. And then we're going to multiply by 100 because it's a percent. So when I calculated that, I got 78.768% tin. And then we're going to repeat for oxygen. So percent oxygen. Be careful with oxygen. There's a 2 here, which means that we have 2 moles of oxygen per every 1 mole of tin. That needs to be accounted for in our numerator. So I'm going to do 15.999, the mass of oxygen from the periodic table, times 2 divided by 150.708 grams. When you're plugging this into your calculator, make sure you put a parentheses around that top value, or you may or may not get the right value without the parentheses. Here I got, we need to multiply that by 100, because it's a percent. And I obtain 21.232% oxygen. Officially, we're done with the problem. What I do like about these problems is that we can check our algebra and our math. All of the percentages have to add up to 100%. So if we do 78.768 plus 21.232, let me do some quick math here. So we'll do 0, carry the 1, 0, we have another 1, 0, carry the 1. So this is just working out great. This is going to be exactly 100% when I add the 78.768 and the 21.232. You want to get close to 100%. Sometimes because of rounding and stuff, you wind up with like 99.99%, which is great. You know you did the problem right. But if you add those things up and you're only at 87%, then go back, redo it, check your work. Maybe you didn't multiply or something like that. This problem is really similar to our previous problem. We need to start by calculating the molar mass of the cinnamonic alcohol. So from the formula, I know that there's 9 carbons. And I'm just grabbing the masses off the periodic table. So 12.011 grams times 9, 10 hydrogens. And just 1 oxygen. For a grand total of 134.177 grams. The molar mass in this type of problem is going to serve as our denominator. It's the whole in the part over whole formula. The part is going to be each specific component. So if I'm doing the percent composition by mass of carbon, since there's 9 carbons, I'm going to do 12.011 times 9 divided by 134.177 grams. That molar mass that we just calculated. Multiply by 100. And I'm at 80.564%. Next one, hydrogen. Same deal, there's 10 hydrogen, so I need to do the mass times 10. And I'll multiply that by 100%. Sorry, I'm probably blocking your view. Make sure you're using the parentheses again in your calculator. 7.5117%. The last one is going to be our oxygen. So there's just one oxygen, so I can just do 15.999 grams divided by our molar mass. And we'll multiply by 100. Get 11.924% oxygen. Looking at the unit, right? The units on our answers are percent because grams cancel with grams. So you could do this problem in kilograms, but make sure you have kilograms in the top and kilograms on the bottom. Your units, whatever you're plugging into the part over whole part, needs to cancel, and you're just left with percents. Before I end this little segment, I always like to check that I did my algebra right. And the best way to do that is to add up all 3 percentages. So if I grab my calculator here and I add up 80.564 and 7.5117 and 11.924, I get 99.9997%. So that tells me that, or it's a good indication that I set up the problem correctly. I want it to be 100% or really close to 100% when I calculate those individual percentages. All right, so the next part of problem number 2 is a little bit different. It's kind of a throwback problem from our previous lectures. We're asked to figure out how many moles of the cinnamonic alcohol are in this mass. So remember, whenever we're trying to go anywhere, our first step is to convert to moles. So I'm going to do 0.469 grams. And we want to be really specific here. So I'm going to do C9H10O. And I want to get rid of the grams. So I'll put that in the denominator of my conversion factor. And I want to try to go to moles. So 1 mole, and then I'll grab the molar mass that we calculated in our previous step. So 134.177 grams. Let's look how everything's canceling so far. So grams will cancel with grams. Now we need to get rid of the moles of the cinnamonic alcohol. So I'll put another conversion factor. And here we can use Avogadro's numbers. So we'll put 6.02 times 10 to the 23rd molecules of C9H10O. All right, so everything's canceling. We're just left with molecules of cinnamonic alcohol, which was our goal. I'll do, in my calculator, I'll do 0.469 times 6.02 times 10 to the 23rd divided by the molar mass. And I got 2.10 times 10 to the 22nd molecules of cinnamonic alcohol. So in part C, we're asked to consider individual hydrogen atoms. Again, always start with the number they gave you and look to use conversion factors. So you have 2.12 grams of C9H10O. Whenever you're stuck, always consider going to moles because moles is the bridge to wherever we want to go. I'm looking to get rid of grams, so I'll put that in the denominator. And I'll change that into moles. This relationship is going to be our molar mass. So 134.177. Grams is going to cancel grams. Now, I'm thinking about this, and they don't want to know about the cinnamonic alcohol. They don't want to know about C9H10O as a whole. They just want us to figure out how many hydrogen atoms individually. So it would be great if I could get rid of moles of C9H10O. And maybe go to moles of hydrogen. This relationship, the relationship between moles of hydrogen and moles of a compound as a whole, is defined by the formula. So one of these, 1 mole, will have 10 moles of hydrogen. Kind of think of it as like a Lego set or something, and if we had built this molecule, we would need to grab 10 hydrogen atoms or 10 hydrogen Legos or whatever's representing hydrogen on our set. So we're building one massive thing, but it has 10 of these in it. So that's where this is coming from. So moles of this will cancel moles of this. We're not at the level of atoms yet, right? Moles is just a counting unit. So now my next one will be to get rid of moles of hydrogen. And using Avogadro's number, now I can change that into atoms of hydrogen. And 3 sig figs, because that's what our original number had, and this is exact. I'll do 9.51 times 10 to the 22nd. Ooh, let me check my units. So we got rid of the moles of the cinnamonic alcohol. That last conversion factor got rid of the moles of hydrogen. And so we're just left with hydrogen atoms. There you go. There are so many parts to this problem. It's deceptively short. First things first, we're given a written name for the compound. So we need to convert the written name to a formula. So remember, the Roman numeral stands for the charge on the metal. So we're going to do iron 3+, and we have an oxide, which refers to oxygen. So it's going to be O, and we know it's 2- because it's in group 6. So we're going to take those charges and crisscross them down. And we get a formula of Fe2O3 for our iron 3 oxide. The problem is asking us to figure out what mass in grams of this compound has the 58.7 grams of iron. So I'm really honing in on the iron here. For this problem, I need the mass percent of iron in the iron oxide. Just like our previous 2 problems, we're going to start that by calculating the molar mass. So we have 2 irons. 3 oxygens. Multiply, add that up, and we get a molar mass of 159.687 grams for the iron oxide. Again, let's focus in on iron here, since the problem is asking us to compare iron to iron oxide. So to calculate my percent iron, I'm going to do the part that's iron. So I'll do 55.845 times 2. And part over whole. The whole part is 159.687 grams. Multiply that by 100. And we're looking at 69.94% iron. When we calculate a mass percent, we can convert that, or we can think of that as a conversion factor. So with this 69.94% iron, I'm thinking about 2 versions of the conversion factor, and percent means out of 100. So I can interpret this to mean, well, if I had 69.94 grams of iron, I would have 100 grams of iron oxide. Or I might be thinking it the opposite way, but it's the same difference at the end of the day. We're thinking the same thing. We could flip that, and we could think, well, if I had 100 grams of iron oxide, I would expect 69.94 grams of iron. So at this point, I get a lot of students who are really good at algebra, really good at percent calculations. Do I have to use conversion factors? Absolutely not. If you can solve this type of problem and get the correct answer over and over again, do your way. I like this because I was never a big fan of percentages myself, and conversion factors just made more sense to me when I started learning chemistry. So I like to present it this way, just to give students an alternative. So like all conversion factor problems, we're going to start with the number they gave us, so 58.7 grams. And that's grams of iron. So we're looking to get rid of the grams of iron and figure out the grams of the iron oxide. And so right over here, we'll use that second one, right? So if we had 100 grams of iron oxide, it would be 69.94 grams of iron. Grams of iron cancel grams of iron. So in my calculator, I'm going to do 58.7 times 100 divided by 69.94, and we'll get 83.9 grams of the iron oxide. Alright, so last problem of this set. Here we're told that we have 47.1% by mass oxygen. We're dealing with a binary compound. It's just aluminum and oxygen. So the following relationship holds true. We know that the percent of aluminum by mass, so percent by mass aluminum, plus the percent by mass oxygen has to equal 100%. That's critical because in part A, they want me to solve for the mass percent aluminum. So I can take 100% and subtract the 47.1% that's associated with the oxygen. And then at that point, I know I'm dealing with 52.9% by mass aluminum. That gives me 2 conversion factors. That's my answer to part A. But then at that point, I'm thinking about two different conversion factors. Thinking if I have 100 grams of this compound, I expect to have 52.9 grams of aluminum. Or we could flip that. If we have 52.9 grams of aluminum, we'd expect to see 100 grams of compound. And again, so from our mass percents, we can pull out conversion factors. So part B is going to look like any conversion factor problem. We're going to start with what they gave us. So 112.6 grams. And be really careful here. Grams of what? So gram sample of this compound. So I'm going to write compound here. And then I'm like, okay, well, I want to get rid of grams of compound. So let me throw that in the denominator. And I would like to solve for the mass of aluminum. So grams of aluminum up here. Looks like this second conversion factor fits better. So 52.9 grams of aluminum for 100 grams of compound. Now, as you can see, grams of compound cancel grams of compound, and then we're just left with grams of aluminum, which is perfect because that's what they asked us for. So 59.6 grams of aluminum. That would be my answer to part B. I got that by doing 112.6 times 52.9 divided by 100.